Mathematical modeling of reactive transport of contaminants in heterogeneous flow of saturated and unsaturated media. Abstract: in this paper, an analytical first-order solution to the one-dimensional advection dispersion equation. With adsorption term C1et to study the transport of 2. Mathematical model. The advection dispersion equation along with initial conditions and boundary conditions can be written as: pollutant vary exponentially with time using a generalized integral transform method. In this chapter, we have investigated the transport of pollutant for adsorbing medium and non-adsorbing for reactive and non-reactive flow of saturated and unsaturated porous media. The solution is derived under conditions of steady-state flow and arbitrary initial and inlet boundary conditions using Duamel's theorem and integral transform methods. Keywords: integral transforms method, mathematical modeling, advection dispersion equation, saturated porous media, unsaturated porous media, heterogeneous flow. Introduction. In this study, the advection dispersion equation has been resolved by using analytical methods to measure the solute transport of contaminants by considering the porosity and dissipation coefficient using input concentrations. The advection dispersion equation has been extensively used in simulation and modeling of reactive transference in groundwater. The convection dispersion Baer, 1979, Gelhar, 1973, Domenico, 1998, Fetter, 1999, Sudheendra, 2010, 2011, included hydrodynamic dispersion, advection, adsorption, first-order decay reaction, and possibly zeroth-order production. Analytical solutions are generally derived from the basic physical principles and different from numerical dispersion. The other truncation errors usually occur in numerical simulations. Zheng and Bennett, 1995. Consider a semi-infinite porous medium in a unidirectional flow field in which the input tracer concentration is C1et, where C0 is a reference concentration and is a constant as shown in the following figure. 1. Figure 1, schematic representation of semi-infinite porous medium in unidirectional flow field. Source concentrations is hence the suitable boundary conditions for the given model. The solutions of one-dimensional advection dispersion equation have been examined in many previously and are still actively studied. For example, Sauti, 1980, and Van Genuchten, 1981, Sudheendra, 2014, have been providing analytical solutions of the solute transference equation with the first, second, and third type boundary conditions. 1981, has given by analytical method and computer code for assessing the waste transportation in groundwater aquifers. Then the problem is describe the concentration as a function of Z and T, where the input condition is supposed at the source and a second type condition is supposed. C0 is initial concentration. To reduce equation 3, in a more conversant form, we take by Duamel's theorem, the result of the problem with C00 and the time-dependent surface condition at Z equals 0 is. By substituting equation 3 in 1, we get. Since E2 is a constant function, it becomes the initial conditions and boundary conditions transform. The solution to the problem is equation 4 can be resolved for a time-dependent arrival of the fluid at Z equals 0. The solution of equation 4 can be attained quickly by use of Duamel's theorem, the same method already been used in the previous chapters. The inverse Laplace transform of the given function using the table. The result is. For convenience, the second integral can state in terms of the error function, thus the function was perfectly tabulated. Observing that only by considering the first term of equation 11, let realistically in figures 5 to 9. Figures 5 to 9 represent the breakthrough curves for C/COVS time for different depth Z. It is seen that the concentration field increases in the initial and reaches a constant state value for a static Z but decreases with an increase in the layer width. Similar pattern is observed in figures 5 to 9 for distinct values of W and D. Figures 5 to 9 represent the breakthrough curves for C/C0, and is maximum at the surface Z equals 0 and decreases to reaches 0 at the depth of 100 meters. With an increase in most of the contaminants get absorbed by the solid surface and thus suspending the movements of the contaminants as evident from the graphs. The majority of the pollutants are reduced in. Where boundaries are symmetrical, then the solution of problem is specified by the first term in equation 18 and 21, and the second term in equation 18 and 22 is thus due to the asymmetric boundary imposed in the more general problem. Though, it should also be noted that if a point an immense distance away from the basis is measured, then it is probable to estimate the boundary condition by TC0, which tends to a symmetrical solution. 6. Results and discussions. This water finally enters the groundwater storage basin, a basis for drinking water. Throughout the passageway of water through the soil, the pollution is combined, and then mixing takes place in the soil medium by two processes, viz., molecular diffusion and dispersion. Molecular diffusion is a physical process, which depends upon the kinetic properties of the fluid particles and causes mixing at the contact front between the two fluids. Dispersion, however, is defined as a mechanical mixing process caused by the twisting path followed by the fluid owing in the geometrically complex interconnections of the flow channels and by the variations in equations relating to solute transport are resolved analytically and numerically. Analytical solutions for the one-dimensional model are obtained using Laplace transformation techniques. To estimate the magnitude of the danger posed by some of these chemicals, it is important to investigate the processes that control their movement from the soil surface through the root zone down to the groundwater table. At present, foremost drive on the transportation of pollutants and research is directed towards the definition and quantification of the process governing the behavior of pollutants in subsurface environment, combined with the development of mathematical models that integrate process descriptions with the pollutant properties and site characteristics. From the equation 18 and 22, C/C0 was numerically computed using Mathematica and the outcomes are presented.